Oh, we can feel the end, almost. We're in rule number 4, the final rule in our rulebook. Drop non-dominants, or drop non-dominant terms. What do we mean? Let's have a look. Let's say we have a function, again, with a really long name that says print all numbers, then all pair sums. Maybe not the best name for a function. We can probably work on the readability here, but let's see what this function does. Well, this function takes numbers, and these numbers variable, we're going to loop over them with a for each loop. So again, just looping over and logging out the numbers. And then we have another step, which should remind you, that's probably an addition that we're doing. We're adding another step. And in here, we're summing the pair sums. That is, we're adding each number one after another. Let's show you with a little bit of a demo here. If, let's say, we create, actually, we'll just print numbers. And in here, for the numbers, let's just give it an array of 1, 2, 3, 4, 5. If I click run here, we see that these are the numbers 1, 2, 3, 4, 5, because this is the step. We're just logging it out, nothing too difficult. And these are their sums. All we're doing is adding 1 with 1, then 1 with 2, which equals 3, 1 with 3, which equals 4, 1 with 4, which equals 5, and 1 and 5, which equals 6. And then we move on to the next loop, which is 2 and 1, which equals 3, 2 and 2, which equals 4, and it keeps going on and on and on. So we see the loops that we've done here. And problems like this is something we're going to do later on in the course. Right now, we're just worried about big O. What do you think the big O notation here is? Well, once again, if we do O of the first part is the for loop. So we can say that there's O of n. And then the second part, which again is another step. So we're going to say add plus. This one has 2 for loops nested. So that means O to the power of 2. All right, so that's our big O notation. But rule number 4 states that we want to drop the non-dominant terms. That means we care about the most important term. In this case, we actually drop the n and just have n to the power of 2 because as the input increases, the size of n to the power of 2 is way more important than the n. So we always just keep the dominant term. Let me give you another example. What if we had a function that had a big O of, let's say, x to the power of 2, and then we'll say that it has 3x plus 1,000, and maybe we'll say plus x divided by 2. All right, that's really, really confusing. That's math. We're not gonna want to deal with that too much. How do we simplify this based on the drop non-dominant terms? The 4th rule states that, again, we worry about the most important dominant term because x to the power of 2 is the most significant. That is, if x is 5, 5 to the power of 2 is 25. 5 times 3 is 15. This is 100. And 5 divided by 2 is 2.5. In this case, the dominant term is 100. But remember, with big O, we're worried about scale. And as things grow larger and larger and larger. So when this becomes 5,000, well, 5,000 to the power of 2, or 500 to the power of 2, that's 250,000, if I did the math right. 3 times 500 is only 1,500. 100 is now insignificant, and 500 divided by 2 is 250. You see how this has grown significantly more? Again, because we're only worried about scale here, we drop everything else and we can just ignore it completely, and this becomes x to the power of 2. How nice is that? Just makes things so much simpler. So there you have it. We have now a way to simplify everything. If we go back to our past examples, remember this one? Remember this one? It now makes sense why we've just said big O of n, because we don't care about the insignificant items, only the most important ones. And same with this one. By the way, a fun little note here. If we had another loop inside of these 2 loops, well, this would become O to the power of x cubed, and cubed doesn't really matter what we have, but it's going to be to the power of 3 because we have 3 nested layers. And you can keep going. You can have to the power of 4, to the power of 5. But here's the thing. If you have 3 nested loops, 99.99% of the time, that's usually a bad idea. It scales really, really badly, and most likely you're doing something wrong. And there you have it. We've gone over the 4 rules. And with this in mind, we're going to take a look at the cheat sheet that I've prepared for you. So from now on, instead of having to calculate everything and really look at every single detail of a function, you can right away figure out what the big O is, or what the time complexity of a function is.